Okay, well, welcome to our next lecture in Computer Science 2120 and Software Design and Development 2, where we're effectively using Java in a more advanced way. So in our prior lectures, we learned how to effectively use interfaces, and then we learned about design by contract. We learned about preconditions and postconditions, and then we learned about how we can build our own, render our own API that we can share with other developers using Java Docs, which is a tool that's been around for as long as Java has to produce that API documentation you've seen before. Now you can do that on your own. So in this lecture today, I want to focus on testing, and in particular unit testing, and I want to introduce a new tool called JUnit, which will allow us to do unit testing with Java. And so today's lecture, there's a lot of critical concepts that I want to ensure that everyone is familiar with in terms of what is testing, distinctions between things like testing and debugging, what are the different forms of testing that exist, because in this class, we'll make use primarily of unit testing. But in 1583, when you were submitting your code through AutoLab, you were effectively performing functional testing. So I want to compare and contrast those approaches a little bit. And then finally, I want to make sure that everyone has a clear understanding about what JUnit is and how JUnit works. So this first lecture on testing is going to likely be relatively slide heavy, simply because there's a lot of core theoretical concepts that are pretty critical for you to understand the importance of testing and how you'll actually put it into practice. And then once we get through the slides, I want to spend some lecture time using IntelliJ to actually perform this testing so you can see how it actually works. Excellent. So let's move on. So the first part of the lecture will just focus on testing itself. So let's talk about the importance of testing. Testing is ubiquitous and it's expensive software engineering activity. It's not unusual to spend 30 to 40% of a total project effort on testing. I mean, this is an industry that's a large part of the process of developing goes into testing. But that should make sense. I don't know if this was hammered into you early on, but typically in an iterative development cycle, it's broken into 3 different phases. You have a design phase, you have an implementation phase, and you have a testing phase. So whenever you start building out your software, typically you start with something that's relatively simple and you keep adding complexity on top of that. And for each time that you're considering adding a new thing, you want to design it before you implement it, and then you want to test it after. You want to design before you implement it, then you want to test it after you implement it, before moving on to the next step. And so, yeah, that makes sense, because if it's a third of your development cycle, it's going to take up about 30 to 40% of your project efforts. But it's super valuable, because if you don't spend that time testing, it could take much more time for debugging. So for big and or life critical systems like flight controls, testing costs can be several times the cost of all other software engineering activities combined, but that's because it's worth the investment. For life critical systems, you can't afford for them not to work correctly. And there's some very famous instances that have occurred where several hundreds of millions of dollars were lost or lives were lost because of simple bugs that appeared in code. And we're talking about bugs that like cause rockets to fire at the wrong trajectory while exiting the atmosphere, blowing up the rocket and the satellite that was supposed to deploy, or like an X-ray machine. I think it was called the Thorac-25, if memory serves me correctly, where unfortunately it was because of a programming issue was allowed to use more radiation than it should have, thereby inflicting cancer on the patients. So there's real life cost in some of these systems when testing isn't done appropriately and properly. So fortunately, in the realm of computer science, we exist in digital spaces. So when we make a mistake, we're just like, let me change that variable and recompile. But there are some systems supported by software where it is much more mission critical to get it right the first time. And there's real consequences for delivering bad or faulty software. But we should always highlight the importance of testing, even though we're not in the hard engineerings where if you only get one opportunity to build a bridge, right? Fortunately, most of our tasks aren't like that important where there's a lot of foreplanning that goes into it. It's still important to be a part of, to perform these testing as if it was life or death. Okay, let's talk a little bit about the different types of testing. So this has two main types, and I guess this is true in the idea that there's two different ways we can test in what we experience, what we've done so far. So like in the first Java class in Software Design and Development 1, you were performing functional testing. Whether you realized it or not, that's what you were doing. Because what was happening was you produce some code based off of some input, you would generate output. And so with functional testing, given some input, it does the software system as a whole produces correct output. And so this is referred to as black box testing, because as you probably realized, Autolab didn't care how you implemented your solution, just that when it fed that input, it produced the output that it expected. And if it did, you got the full points for those solutions. And so, yeah, that's a functional testing approach. An alternate approach to that, and this is the approach that we're going to be examining during this semester, is going to be called unit testing. And so for unit testing, you do this for each of the individual components of your software system, and you ensure that each individual component behaves properly. So the big distinction here is we can think about this as what's commonly referred to as black box testing versus white box testing. And then there's actually these shades of gray that happen in between. But let's talk about the two extremes. So white box testing, which could also be considered implementation-driven testing, is where we have full access to the code we're testing. And so, and what I mean full access is like, unlike Autolab that could potentially just have an executable, in white box testing, we have to be able to see the source code and have it available so that we can decouple it and test it at elemental pieces. So we can use the code to get an idea of how to test it. Often development driven by the authors of the code being tested. So typically this approach, this implementation driven test approach, is the approach you would take as the developer itself to ensure that what you implemented is working the way you expect it to. So again, white box testing is typically the type of testing you do in that classical design cycle that I was talking about earlier, where there's a design step, then there's an implementation step, and then there's a testing step. The testing step validates and verifies that your implementation is in line with what the specifications were. Now, black box testing is functional testing. This is where you only have the documentation for the source code. And so you test the code using what we expect to happen based off of the class's contracts. And then we have gray box testing, which is a test-driven implementation where we have the source, but we haven't implemented it yet. So we build the test before we build the actual source code, and then we write the code to pass the test. Excellent. So let's talk a little bit about how with unit testing. So we mentioned here there are two forms of testing. Unit testing deals really well with scale, whereas functional testing doesn't. So one of the best practices is to test individual units or components of your software, where one class with one method at a time. And again, this is called unit testing, and the unit is because the unit is the elemental part of the software system that we're evaluating. So as we build up these parts, we rename the to different testing types. So you might have heard the terminology of integration testing or system testing as well. So with integration testing, Testing that happens when you have multiple components that are put together into a larger system is your integration testing, and testing on a whole end user system is system testing. So that kind of gives you the idea of how it gradually expands out. And ultimately, when you're developing, you have to ensure that your entire system is going to be performant and not crash before you deploy it. So it's important that you, while building it, use unit testing. And then when you put your different units together, you do your integration testing to make sure no conflicts or domino or butterfly effects happen there. And then finally, you have to make sure the entire system is able to operate on its own once everything's been integrated together. Okay, so let's talk about the role of testing in individual environments. And I put role here, but maybe a better word here would be motivation. The motivations of testing in an individual environment. Well, so let's reflect back on that software design cycle I was talking about. After designing a solution to a problem and implementing, the role of testing is to verify that your approach to a solution works as expected. So that's one reason why you want to test. You want to make sure that at each step of the evolution of your software, it's working as expected. So whenever a bug happens, you know where to look to try to correct it. If you never test and you just produce code all the way to the very end and you go to compile and you get like 1,000 compiler errors, that's going to be a nightmare to try to go ahead and fix. And you're going to spend more time debugging than you would have spent testing from the get-go. Testing is partly what makes computer science a science as well. That's what I would argue, right? Like if you think about what is science, well, you make a prediction, you look at the results, right? And you evaluate the results, and then you try to predict if the result is something outside of your hypothesis, you try to explain why. And then create a better solution on top of that. And kind of keep building off of your knowledge base. So without verifying your results as you're building out your algorithms, it can lead to unforeseen erroneous behavior. And that's what you want to avoid. So testing tests what you predict to be your solution. And so it's putting the science into computer science. So we should endeavor to do that. Okay, so let's talk about the motivation of testing in team-based environments. So here, I'm going to change the word choice here, motivation. I think that's a better word for what I'm trying to capture. So an innate problem in any team-based coding endeavor is that it's distributed, right? So if you're working at a company and there's a team of developers, conceptually, all the team has to come together and they're working on the same project at the same time. And so typically a team can consist of multiple members of varying roles. So like you might have your software architect who communicates with a team of lead developers, who then themselves communicate with pods of junior developers. And so the workload of coding whatever the project is has to be divided up across all those people. And so you could see where the complexity there is. It's like, how can you ensure that everyone is on the same page, that everyone understands the complexity of the system? You can't guarantee that. And if you assume that everyone understands what they're supposed to do and how it's supposed to be implemented, then that approach is doomed to failure. And you're going to create buggy software that's not going to work well. And it's going to go into a developmental hell, for lack of a better term. So the solution to this distributed problem is in testing. Most of the team only needs a small understanding of the system. They don't need a complete understanding. So each member who is an implementer of a part of the system could be clients to the rest of the system, where they don't need to know the details. They just need to know what the contract is via the design by contract. They just need to know what methods exist and what data they send to the methods they might need for their own software and what it's going to produce back as results. So thus the system is broken actually into several small class method APIs. And to ensure that each developer understands their contracts for what they're responsible for. So that's identifying what their preconditions and postconditions are. The first task, usually between the junior developer to the lead developer, or between the lead developer and the architect, is to build test cases. Because when the junior developer is talking to their lead developer, they prove that they understand the class they're supposed to design and the methods that class is supposed to support by saying, these are the test cases. Given this input, this is what I think the output should be. And then given that input, once they have those input outputs, once they have an understanding of what the result of their implementation should be, then they can start figuring out how to get from that input state to that output state. They can figure out the implementation details in between. They can develop the code after they've created the test, because the test cases allow them to understand how you get from point A to point B before navigating a trajectory between those two. And then the goal for the junior developer is simply to make software that can pass the test. And as soon as the software passes the test, then that software can be integrated, go into the integration testing phase, where it can then be part of the software system as a whole. And so the tests are supposed to represent, it's supposed to mock the way that the classes and methods are going to be used by the rest of the software system. And what's great about this is it allows you to concurrently develop classes that rely on each other at the same time without those classes existing yet, because you can mock the data as input, and then you can produce the output and say, if this works inside of my virtualized fictional, mocked out environment, then I know when I put this into deployment, when I put this into the real system, it should also work. So the purpose, right, then the role here is that it helps us assign responsibility across the dev team. If the submitted code does break the system, but it passed all of the approved testing, then the fault isn't with the developer, it's with the manager for approving that test set. As that test set was supposed to be representative, that marked data set was supposed to be representative of the actual usage of the class and method in the deployed state and the deployed environment, the software system. And so this is a means of allowing everyone to be on the same page and understand what their role is in contributing towards the software system as a whole. So you can see why testing is very important, especially once you get into industry and inside the professional realm. So let's talk about testing functional correctness. What does it mean for a program unit, let's say a method, for instance, to be correct? Well, it does what it's supposed to do, right? And it doesn't do what it's not supposed to do. So it's pretty easy conceptually to define what correctness should be. So what does supposed to do actually mean, though? Well, how do we know what a method is supposed to do and what is it not supposed to do? And so again, what we look towards understanding how a method, what it's supposed to do and not supposed to do, is that contract that we talked about previously, which serves as our specification of intended behavior. So let's talk about behaviors. I'm going to do a Venn diagram here to try to visualize this. So suppose you have all of the allowed behaviors of the method. So here, this would be what's defined by our contract. So your contract will claim every valid value that can be supplied to the method. Now, inside the Venn diagram, when you go to produce an implementation, you might implement something that doesn't make use of the entire valid set. It might just use a subset of the behaviors in that method. And this would be the implementation. This would be the body. So often the case is the theoretical valid values is larger than what you actually implement, which ends up just being a subset. But what's super critical is that what your actual method, what your actual implementation is delivering on, exists entirely in the space of what the contract states. So you can have a full one-to-one mapping. The orange could completely fill the green, and that would be okay. What would not be okay is if the implementation falls out of the green Venn oval. So if at any time you breach that boundary point, then that falls outside of the contract. And that's not allowable. That's a violation. That's what will cause issues and erroneous behavior. So for each point in this space is a legal input with a corresponding allowable result. So again, let's take an example look at a method contract. So here we have our at requires, so that's our precondition. We have our at ensures, that's our postcondition. Our precondition here says that n has to be greater than 0. And then our postcondition, what we're guaranteeing then to our client is that our a factor will be greater than 0 and n mod a factor will be equal to 0. And so if we look at the method signature here, we can see that we're going to take in the n from the end user. And so what do we mean by n mod a factor is equal to 0? Here, this just means that n is divisible by a factor. So we'll use this as a base case to see. Now let's implement this, and let's implement this in like in a way that it captures some of the space that is valid, but not all of it. So here we're going to create a factor where it takes in an n and it's just going to return a 1 because all numbers are divisible by 1, right? Okay. So is the method body correct? So let's see actually. So if this is the claim, this is the question, right? We're looking for correctness here. So what we can start doing is we test it. So we have our full allowable behaviors based off of our contract, and then based off our implementation, we might fall into here. But the important thing is that we're always inside the green. We never fall outside that green. So let's say n is equal to 12 and 8 factor is equal to 4. That's valid, right? Like 12 is divisible by 4. It has a modulus remainder of 0. So that would fall into our green space, right? If given 12 and if a factor is 4, that works. That supplies what the original contract was. However, if we're given 12 and we say a factor of 12 is 5, well, that's not right, right? That produces a mod value of 1. So that violates the post condition. So if our software gave that as a result, it would not be fulfilling our contract. Now, if we were given 12 and a factor of 6, that falls into the green. None of this has fallen into our implementation, but that's okay, right? Here, and it'll be 12 and our a factor is 1. We're returning 1. That fits into this green space, right? Like, again, 12 mod, yeah, 12 is divisible into 1. So the body is correct if actual is a subset of allow. Okay, so now that we've kind of looked into this question of, is our body correct? Let's see if given inputs, all of our output falls in the expected claimed range. Let's revisit this idea of implements for interfaces. So if we write a class C that implements an interface I, the Java compiler checks that for each method in our interface, there is some method body for it in our class. We really care much more that for each method in our interface, the method body for it in our class is correct in the sense just defined above, that the results fall into the valid space and that it never falls outside that valid space. So how can you decide whether this is the case for a given method body? Well, again, we have to test it, right? Testing is a technique for trying to refute the claim that a method body is correct for the method contract. In other words, the goal of testing is to show that the method body does not correctly implement the contract, i.e. that it is defective. And as a tester, you really want to try to think this way. And by the way, if you enjoy this approach of trying to find ways, trying to think of clever ways to break a method, that's completely what cybersecurity is all about. Trying to test the vulnerabilities of where software might be at its most brittle, where you can compromise and do things that it wasn't intended to do. So this can kind of give you one of your first kind of inputs, one of your first kind of views into what a cybersecurity professional could do. So the psychology of testing is as so. You want to design, and design and coding are creative activities, but testing is a destructive activity. The primary goal of testing is to try to break the software, not try to make the software. So you're trying to show the defects of it. So very often, the same person has to do both. They have to create code and they have to break their code, which typically you don't want to think of as a best practice, but it is. Like, your code is only going to be robust when you think of all the edge cases that could potentially break it. But at the same time, you have to kind of have this split personality for yourself, where you're trying to push your feature set, but then you also want to reel it in and say, well, how could I potentially break based off of this implementation? And again, those are two different steps. There's the creation step, which is the implementation phase. And then separate from that is your testing step, where you try to break it. So don't try to do those two activities of creating software and then evaluating it at the same time. Much like what one does as a creative writer, you first start by drafting out your story notes, and then you go into an editing mode to improve what's clumsy or awkward or not needed, or what doesn't work to facilitate the story. So you could think of testing as a form of editing. So let's talk about testing versus debugging. So I know I've used these terms throughout my explanation so far. So the goal of testing is, given some code, you want to show by executing it that it has a defect, i.e. there's at least one situation where the code's actual behavior is not an allowed behavior. Whereas the goal of debugging is, given some source code that has a defect, you have to find the defect and repair it. So it is better to test than to constantly be debugging, because you wouldn't have to debug if you had properly tested, or that's hopefully happens most of the time. Sometimes there are these edge cases that are so hard to detect that they crop up, and then you just have to debug to find it. But most often the case that any time that you put in testing is well worth it. It's a tenth of the time you would spend debugging by just ignoring the testing. Okay, so let's talk about incorrect or defective code. So if actual behaviors are not a subset of the allowed, then this is what it would actually visually look like. So in our Venn diagram here, our green space represents all of the allowable behavior based off of our contract. And then our implementation illustrates where we violated that contract, and we produce output some of the times that falls out of a valid that breaks the contract and produces an invalid result. So when we test, when we start testing, so this is our implementation before testing, and as we test, we put in our inputs and we observe the results. And so it might be, you'll see most of the space inside of this visualization exists inside of the allowable space. So many of our tests will appear to be correct, that our software is working based off of the contract that we've specified. However, one might lie outside the allowed behaviors, and so that's what you're looking for. If this happens, testing has succeeded in revealing a defect in your method body that you then have to go back and correct. So test cases. Each input value and corresponding allowed expected result is what's called a test case. Test cases that do not reveal a defect in the code do not help us refute a claim of correctness, right? So it's just working as you expected it to work. And so one of the things it falls completely in line, and one of the things I always usually tell my classes, where you should always be happy when you get something wrong. You should never be happy if every time you tried to do something, it worked exactly the way you thought it would, because that means you've never learned anything. That means you're just doing things you already know how to do. And so testing, if all your test cases just produce the result you expected it to, then you haven't learned anything new about your software system. So it's those instances where it failed that you identified something that you're going to learn from, that you're going to correct and harden your software in a sense. So the test cases where things do go wrong, those are good. Those should be cherished. You should not avoid those. You shouldn't just test the easy, low-hanging fruit. So you want to have a test plan and a test fixture. A set of test cases for a given unit is what's called a test plan or a test fixture for that unit. And so for correct code, if actual behaviors are a subset of the allowed, right, then that's what we'll define as correct code. And so as we start trying some inputs and observing the results, it'll always fall into that green space, and then we will never find a defect. However, understand there is a limitation to testing, because program testing can be used only to show the presence of bugs, but you can never use it to prove the absence of it, right? You can't prove the negatives of something. So now that we've talked about the importance of testing and what it means to test, and we defined what a test plan is, let's talk about what it takes to design a test plan. So to make testing most likely to succeed, because that's what you're trying to do, just like you're trying to architect, just like you're trying to design a software system, you also have to design effective test plans. So to be successful in trying to revealing defects, there are a set of best practices you can use. So you want to test the boundary cases, which is going to be the smallest thing that your contract claims. You want to test the largest cases, so that'd be like the largest value that your contract claims to support. And then you'd want to test like those special cases based on the contract that can cause potential issues. Like, let's think, for instance, if you were doing a date class and you're testing that. So like the boundary cases would be like the first of a month or the last of a month. The special cases, the special values would be like February, for instance. Like, is it a leap year or not? Then you always also want to test the routine cases. These are the ones that your system's most commonly going to have to deal with. You want to make sure those are working adequately. Like, don't only test the boundary cases, because there might be a flaw in your logic that affects the routine cases. And so you always want to test your software the way it's going to be used most often. And then finally, you want to try to test the challenging cases. And what do we mean by challenging cases? Well, those are the ones that if you were writing the code, because maybe you didn't write the code being tested, but if you did, you'd want to find those parts of the problem that would be difficult to implement, or the ones that would be most prone to error. And so when you're thinking about what method you're calling, try to feed it data that would cause that error to occur. So these are like the three kinds of classifications of test cases you should try to come up with in your test plan. So again, looking back at an example method for this contract, our at requires here. So our preconditions claims that n has to be greater than 0. And so our at ensures, our post conditions, claims that a factor has to be greater than 0, and that n mod a factor, that n is divisible in a factor, right? So what we could do to create a test plan to try to identify what are our boundary conditions, what are our routine conditions, and what are our challenging conditions, I can actually create in tabular form. So on my leftmost column for this partial test plan, I would have my set of inputs. For my middle column, I'd have my resulting outputs, results, and then I'd have what I would expect, whether it falls as a boundary condition, whether it falls as a routine condition, or whether it would fall as a challenging condition. So given the explanation we already gave for this method, let's suppose that n is equal to 1. Well, then the result of that is 1. 1 is divisible by 1. But notice that's one of those boundary conditions. That's one of the least conditions. N has to start at 1, right? And so since that is, and also our result, our post condition has to return at least 1, since we're returning an int. So we want to test that. We want to make sure that works. Okay, so let's look at what if n is equal to 2. Then we want to ensure that the factors we produce is going to be 1 and 2, right? So it's divisible in those two ways. So this can be both routine, right? Because it falls inside of the middle of ours, but it could also be considered potentially challenging. Why might it be challenging? It could be a special case. 2 is a prime number, and divisibility on prime numbers can be kind of awkward. It can be kind of clumsy. It can be kind of clunky. What about when n is equal to 4? Well, that's not a prime number, right? However, it is a square. So it could pose as a potentially challenging number to determine the factor of. And then finally, n is equal to 12. Well, the factors of that could be like 1 or 2 or 3 or 4 or 6 or 12. 12 is a composite number. It's not prime. It's not a square. That would represent just a normal routine value that your method might have to handle. But this is a good example of how you might start developing a partial test plan of expected inputs to expected results and identifying whether it is a routine, a boundary, or a challenging condition. Okay, so let's look at a new contract for a method we haven't talked about. So suppose we're going to create a method that decrements the given natural number. So notice natural number is a class. When I look at the method definition here, we have, it's called decrement, doesn't return anything because it's going to actually mutate or update the value itself. And it can do that because natural number is a class, right? It's an object. It's a reference data type. So we're going to pass a reference data type in, and look at this. We have an at updates right inside of our Java doc comment that's going to let the client know, hey, we're going to mutate the state of what we give you. So be aware of that. Our precondition is that, well, if we're going to decrement it, or if we're going to decrease it by 1, well, n has to be greater than 0 because it's a natural number, right? Natural numbers are, they're no value. They have to start at 1 and they go into the positive space. And then at ensures, so that's our post condition. Well, then as long as n is greater than 0, then we will take n and we will subtract it by 1, and that'll be the new set of n. So like hashtag n represents the original state of n, subtract 1, and now this will be the new state of n. So let's develop a partial test plan based off of our preconditions and post conditions that we would then use to build our various test cases from, to actually test out the software to ensure that it works. Again, what we're doing here is test-driven implementation, where we look at the preconditions and post conditions, and we look at the method signature. And before we do any implementation, we start thinking about what are all the inputs and outputs and the potential boundary conditions, so we can consider these things when we start developing, when we start implementing our code base. So on the instance of where n is 1, our result would be 0, right? 1 minus 1 would be 0. That represents a boundary condition. On the instance where n is equal to 2, well, 2 minus 1 would be 1. That's routine, right? There's nothing special happening there. On the instance of 10, the result's going to be 9. Now, consider we're looking at natural number, which is a reference type and not necessarily using integers, not using any of the primitive data type. So depending on how that's implemented inside the code, that might be challenging. Because suppose that one reason why you're modeling this is you want to be able to have a natural number that's so large, it couldn't fit in any normal common register space. So maybe it's being modeled internally as a string. Then you might have this concept of borrowing, going from a two-character value to a single character value, where at your one slot, there was a 0, that all of a sudden becomes a 9, where the concept of borrowing occurs with subtraction. Well, fundamentally, when you learn that as a child, that's a new rule that has to be applied. That could represent a challenging condition that could be error prone. So you'd want to test that. And then if n is 42 and decrements to 41, again, that's just another routine situation. There's nothing novel or interesting happening there, but it should still be tested to ensure that the expected behaviors fall into space. So what about setting n to 0? What about this boundary case, which is on the illegal side of the boundary between legal and illegal inputs, right? Based off of our precondition and postcondition, right? We claimed n had to be greater than 0. And if it is, we will guarantee that our a factor is greater than 0 and that it's divisible, that n will be divisible by our a factor. Well, so the question is, when developing a test plan, do we have to test for the instance where n is equal to 0? And so no, we don't have to test for that, because that's completely worthless. Because if the client gave us n is equal to 0, that violates their condition, the precondition. So they violated the terms of the contract. So we're not obligated to return back anything that's valid, because they didn't give us anything, something valid to begin with. So it violates the requires clause, so it cannot possibly reveal a defect in the method body. So we don't have to test for that. You don't have to test for things outside of the preconditions. So, but that's an important thing to know when developing your test plan. Okay, so that covers at least the concepts that drive unit testing. The next thing I want to do is talk about how we perform unit testing using Java, and how we do unit testing professionally in industry. So JUnit, so let's talk about, but before I talk about JUnit though, I want to talk about how you would test without JUnit, without professional tooling, without having a framework that does this for us. So the testing that you might have already done is what's called primitive testing. So in primitive testing, you write a main method, and in the most primitive testing, you probably even use a command interpreter. So you probably use like a scanner object, use like this console input and output, the system.in and system.out. So the user, or the developer can actually give inputs to their algorithm, and then they print out the results into the terminal to actually see if it's producing what they expect it to. So these are like skeleton tests. Those are probably how you test it inside of your labs or maybe on your homeworks. And so this is fine when you're first starting out and in cases where your projects are small, right? So the tester compares the actual results with the allowed and expected results by inspection. The pros and cons of this is it's simple, it's easy, it's intuitive. It's a way you'd expect to test something because it gives you observability, it gives you surveyability. It's like, let me feed it input and then see what's producing out, what's given back to me. However, there's massive cons with this approach to testing. First of all, it's tedious because you're manually having to type in input and then look at the output, and then you have to determine for each input whether it's right or not. Then the next reason why this is actually error prone, right? Depending on whether you type things incorrectly or not. And then lastly, it's not an automated approach. And so here's sample code of what that might look like, and it's what you'd expect it to look like, where, like, for instance, you might go ahead and use the scanner object to call this method that gives you a command. And while the command's not quit, you'll see if it's equal to I, and then it prompts, it gives a prompt where then you pull that from the scanner in, and then you perform like your increment or decrement, and then you check before the increment and after the increment what the results are. And so what you're doing is you're verifying that an increment had occurred, right? So clearly what we've done all last semester. Now, a more automated form of this, but one that doesn't use JUnit yet, would be still just using like a main method where we're just effectively invoking the code ourselves. We build a main method to contain sets of inputs as expected results in parallel arrays. So we have an array that represents our input values, and then we have an array that has our output values. And then we can create a simple loop in our array that compares the results of our inputs to our outputs. So this automates the process where you're not manually having to type this in, right? So this is better because the process is more automatic. This is effectively kind of what's happening with the auto labs, right? Where the auto lab takes in your program. It has a collection of inputs that it's going to feed your program, and then it's going to produce responses to that based off of if your output is congruent with it expected. But I'm sure you have lots of complaints with AutoLab, right? Like while you were solving problems, it might have said something was wrong and you're like, well, why is it wrong? It doesn't give you a lot of feedback, right? And so this isn't the best approach. And still, it's very laborsome. It's very difficult to do. It could be better. Clearly, it could be better. But a quick example of what that might look like, outside of AutoLab is, again, we have our set of input numbers, and we have our set of results. And then what we might do here is we will create a for loop, and then we will print out what our expected results are, what our inputs are, and then what our expected results are, and if a test failed or if a test passed, right? So we'll check to see if the result produced here is congruent to the result that's inside of the array, right? So if we're looking for a root, we put in the number from this array along with this, which produces a result. It's going to compare this result to the results array, and it's going to see if it's a pass or a fail. But there's some remaining problems with this, right? One new drawback of this approach is that you need to be able to write the values of the arguments and expected results using Java literals in the array initializations. And this does not work for some types where like each set of input values and or expected results must be creating or performed by a series of method calls. Right, so this works at a very shallow level, but often is the case in object-oriented designs in Java applications. There's a series of nested calls that occur, and this approach doesn't do a great job of testing those deeper nested calls. Another drawback of this approach is that if there are multiple allowed results for the given arguments, mere equality checking with actual results doesn't work well either. Think back to our first problem where we had a factor, where given a value, we produced an a factor. Well, that a factor just represented something that was divisible into the given number. Well, you could have a number that's divisible to many different numbers, right? So what happens if we write in the results an array, the expected result is 6. And so when any of the 1, 2, 3, or 6 occur, you can't really test for that. They're all allowed, right? So if you produce one instance, it's potentially possible that you could produce other wrong outputs, but because it selected the one in that input, it kind of can miss edge cases and doesn't capture the full behavior that you're looking for. And so for serious testing, this is why you want to adopt JUnit, which is an industry standard framework for testing Java code. And so you can use this at the terminal. You can use this inside of an integrated developer environment. It's a framework, is one of the, so let's define what a framework is. It's probably the first time probably that we've talked about what a framework is. So a framework is one or more components with holes in them. Holes. So some missing code is what that means. A programmer writes classes following very particular conventions to fill in that missing code. Effectively, what it is a framework is a lot of pre-built code where it's extensible. The missing code is because that's what you have to supply so you can test the code you want to work it on. If it didn't have the holes, you wouldn't have anything to plug your own stuff into to make it to work, to make it work, to use it to validate and verify and test your code. So what you do is use a framework that's mostly implemented for testing, and then you create these classes that define how you test the class you want to evaluate, and then you can run JUnit from your test class, and then it'll validate and verify and tell you whether your test cases are correct or not. and then you can create your test plan using that. So the result of combining the framework code with your own code, with your programmer code, it produces a complete product. So when you hear frameworks, that's what it always means. It means there's a lot of pre-written code, but it's not an application in and of itself. It requires you to supply some code to customize it for the purpose you need it for. Okay, let's talk about automating tests, because that's really what has motivated the requirement, the desire of using JUnit. So typically each class will have one JUnit test, right? Test class associated with it. So let's say, for instance, you have a class animal, then you will test that class animal with something called animal test. It's always particularly convention to call your test class the same thing your class is, but just with the additional word test after it. The test class can then be run at any time. The idea is to write tests that ensure the class is working the way it should, right? Do normal cases work? Do your edge cases work? Where the edge cases are either boundary cases or challenging cases are handled correctly. So if an exception occurs, is the way that you'd expect it to occur. In Java, the units of a class are the things that are being tested. So it's methods that are the units in our unit testing. So when you think unit, think of method. Since methods should be small and serve only a single purpose, they lend themselves well to testing, and a good test class will have multiple tests per method that properly measure if the method is behaving. So you can think of a test class as your test plan. And again, what's really happening in object-oriented design, whether we talked about this or not, it's worth re-mentioning, is all of the data propagation, all of the interactions, all the processing that happens inside of your application is because you have one object or one piece of code communicating with another piece of code by invoking its method. So objects communicate with each other by invoking each other's methods. And what they're doing is they're passing messages between each other. You pass data through the parameters as input from one object to the other, and then that object invokes its method, processes a result, and delivers a response to that request as another form of data, as return data. So that's what you're testing: the interaction, the parameters and results, the preconditions, the postconditions, the contract by which your API is defined. That's why all APIs are also a collection of parameters and return values. And then the descriptions define the preconditions and postconditions. So let's talk about testing. It's a good idea to write your tests such that specific input values are provided and compared against specific expected output values. If the values agree, we can assume that the test is successful. A good test will test each method using multiple test cases specifically chosen to benchmark your edge cases. So we already talked about that conceptually by looking how we can create our test plans in the design sense. So this would be where we actually implement our test plans. So again, the advantages of testing is there's no more testing by hand. We automate that process. We can easily check if a new feature breaks the test. We can allow large new changes to rapidly be made. We could check if change requests from other users break any part of our system. It can be used as a measurement of code stability. It allows us to test pieces individually and then integrate them with other pieces, understanding that they'll probably and very highly likely be able to assemble together nicely, and it helps document and explain the features of the code. When you build out your test, it helps you really make sure you understand what your preconditions and postconditions are, which will then help you define your API using your Java docs. So let's look at a quick example of what a test class might actually look like. So we would import from JUnit. So JUnit's a framework. So we would import from our framework, let's say, for instance, this assert module, and this assert module would have multiple classes inside of it. We might import from our framework a test class. Then when we go to define our test class, let's say the thing we're testing is natural number root. then the name of our test class would be natural number root test. And then we're going to use annotations. Now notice, unlike with Java docs, where our annotations that get converted into HTML documentation is put inside of a comment block, Java can also part annotations as part of your source code as well. So here we have @test, and it actually exists at the same level as all your other code. It's not in a comment. And so for each test method, what the JUnit framework does is it looks for these annotations, and that's what's getting plugged into the whole of it. It sees it when you go to run this natural number root test and you're running it by importing the JUnit test case. Well, JUnit is then going to say, oh, I'm going to use as my methods to test any method that has this annotation of @test. And any method inside the natural number root test that doesn't have that annotation of @test is not going to run. It's going to ignore it. So it only runs those methods that has this annotated label. So these imports let you use JUnit features. The use of a static import allows you to call the static methods of org.junit.assert. This is probably the first time we've seen a static import, by the way. So notice you can use the static keyword during the import phase for static methods, which is what we need to be able to instantiate our own personal unit test for our code, for the code we want to run, without having to qualify their names. Okay, here, a test plan or test fixture, as we labeled before, is going to be a public class so that the JUnit framework can access it, and it's going to have a method with the test case. Each test case is going to be a public void method, right? So that the JUnit framework can invoke it, and it has no parameters. That's super important because the JUnit framework doesn't know how any of our code works. So we can't pass any parameters into here. It's just going to be able to go ahead and invoke these for us. So anything that has to be defined has to be within the body of these tester methods. And then each test case has that @test annotation just before it, as I stated before. There is an easy way to make a new test case, copy, paste another, and then edit slightly. So here we made one test case, and then we checked to see if it was what we expected. Then we made a new one. We checked to see if it's expected. And then we have all these asserts. And these asserts are what's actually deciding whether the tests are correct or not. These assert equals is comparing the expected value to the one that gets processed by our code. So let's look at some basic vocabulary. Here we have our test case. So our test case exercises a single unit of code, normally a method, and a test case normally makes one call to that method. Test cases should be small. It should test one thing, right? So we want to follow that single responsibility, just like methods should only have one job, just like classes should have one job. Test cases should be testing one small thing. And then you just make as many test cases as you need, right? Test cases should be independent of each other. Orthogonal is what they call that in math. And in JUnit, a public method that is annotated with @test will get called. So you can have helper methods in there as well if you needed to, and they can be useful and they won't be part of your testing, provided you don't label them with an @test annotation. So let's talk about test fixture. So it exercises a single class. So a test case tests a method in a class. A test fixture is that class itself. So natural number test, right, for instance. And so it's going to try to test everything inside a single class. It's a collection of test cases. And in JUnit, a class that contains an @test method, right, is going to be considered a test fixture. Okay, JUnit assertion. So there's most of the way that we determine whether a test is good or not, whether it's valid or not, is with assertions. So it's a claim that some Boolean valued expression is true, normally a comparison between an expected result and an actual result, because that's how we're evaluating correctness. If I get my processed result from the method and I have this expected result that I would think is correct, are these equal? And then in order to pass a test case, all the JUnit assertions in the test case have to be true. And when the test case is executed and no errors occurred, that stops the program from executing. So failing the test case means that some JUnit assertion in the test case is false, or it failed to execute. So with our execution model, you have separate instances or objects are created from the JUnit test fixture. So JUnit creates one instance per test case. And the implication of this is that we do not rely on the order of test cases, right? Since each test case is evaluated independently of the other, and we're not sharing data from one to the other, because you don't want to propagate one failed test into your others, right? You don't want to make a series of Christmas lights where as soon as one, like the state of your object goes bad in one instance and it's relied on in every other instance, then everything else would fail. So yeah, the implication here is that we're always creating new instances for every test case. And so JUnit as a framework provides for that, by the way, and we'll see how to do that. JUnit assertion. So two most useful static methods are going to be assert to check actual results against allowed results. And so the ones you'll likely use the most are assert equals, where you give it some expected value and you compare it to the actual value. And so this is going to return something that's true or false, but this return value is then used by the JUnit framework to actually rank your test and report back to you whether your test was successful or not. The other most popular one is probably assert true, where you give it some expression and it determines if it's true or not. So some Boolean expression. So assert equals is good for anything that's not Boolean, right? You compare one number to another number, right? You compare one string to another string, right? Anything that's looking for equality. On the instances of whether it's Boolean or not, you could use assert equals, but the easier approach is just doing an assert true. There's rarely a reason to use any of the dozen other assertion static methods, but you should look at the API. I think I have a slide that shows some of them just so that you're aware of what you could potentially do. But these, yeah, are the most common ones. Time test. What if you're worried about something like an infinite loop? There is the ability to parameterize and add tests with a timeout. So if you're testing and you know that one of the potential edge cases results in something that produces an infinite result, that would prevent your test from succeeding, right? Because your code would get stuck. It would get blocked in that infinite loop. So in this instance, the framework actually supports timing out that test, where you can give a number of milliseconds before the test case is terminated for running too long. And so in this instance, you could do add test, and then as a parameter to that, you can define a timeout being, say, for instance, 100 milliseconds. However, the problem is, how do you know how long enough a test case is to run? And so that is a problem. That's something you have to consider when developing your test plan. But that's, and so some best practices. Well, you want to keep JUnit test fixtures in the same Eclipse project or the same IntelliJ project or the same NetBeans project as your code, but in a separate source folder. So typically what you want to do is you're going to create one directory that's called SRC, and you'll create another directory that's called test. So tests are then included when the project is built, and it helps keep test fixtures consistent with other code. When we do our testing, when we play around, though, we'll probably violate this best practice for initial purposes, but understand that we're violating this. I want to highlight that before we do some real world examples in IntelliJ. Some more best practices you should be aware of is that you want to name your test fixtures consistently. So an example class would be natural number root test. As I mentioned before, that class would be the test class for natural number root. And so this way, it's very clear what you're testing. So name test cases consistently. So example, don't preface your test in front of the class name. And one reason why this makes it more difficult is all of a sudden, since typically classes are ordered alphabetically, this would make it hard to see if you have your test classes for every class that you have defined in your software system. One nice thing about this is you can see your class and then the test for it. With tests, it would just group all of your tests together, and then it becomes very difficult to find each of the individual tests as well. So recommended test case style would be we go ahead and defined our method, right? Public void, and then whatever the test method is. Then we would set up the variables and call the method under test, right? So then we set up all the data, and then we were actually invoking the method that we're trying to evaluate. So if we're testing here, root 3, right? That's what we're going to test here on each of these instances. And then after we produce all of our expected values and our actual values, we would then do all of our assertions. So you essentially do all your data processing, and then you assert, is this one correct? Is this other one correct? Is this third condition, this third test case correct? So sometimes you can write the expected value directly. So you don't have to store it inside of a variable. You can just go ahead and hard code it. Sometimes you might have to explicitly use the toString method, and that's okay. But what might even be better is doing an equals for this, right? So you can do assert equals, and if you're testing this string, you could do the string and then toString this. But probably what would be better is just use the strings equals method and then just do an assert true. And then for writing JUnit, when JUnit is invoked, it will run each of the methods in your test class definition that are marked with the annotation. We've already covered that, but that has to be a big reminder, because if you forget that @test, you'll run your code and then you won't get back any results from that. And so this is probably the first time we're seeing how annotations actually govern how certain parts of your code are fed into a framework. And this isn't just to JUnit. This is how code is selected to get fed into a framework for other popular Java frameworks. So if you were to work in Spring, which is a very popular web applications or applications framework for Java, you use annotations for that to feed your code into that framework as well. So some big things to know about JUnit 5, because that's the current version. That's the latest release of JUnit. Some of the new updates that you want to be aware of is the annotations they have a before all that's going to execute the methods. It'll execute this method before it starts running any test. So if you label a method as before all, you can use it as a setup method. They have an @after all, which would execute this method that's labeled with that after running all of your tasks. So if there's any kind of cleanup stuff you want to do or need to do and evaluate, you can use this after all. So you are giving kind of flow control of deciding what happens before the test, what happens during the test with the @test that indicates that a method is a test method, and what happens after the test. And so they have before all and after all, and that's before running any test, and after all is after running all tests. They also have before each and after each. Before each executes this method before every test. So again, if you wanted to set up a new set of data before every test so that you have that data available, you can do before each. And then that method gets called to reset the values of your instance variables in your test class every time it goes to run a new test case. So before each is a very popular way of setting up data. So you don't have to do what you were seeing before, where you're setting up all this data again and again and again. You can set that up in a setup method, which we'll actually look at in the next lecture when we actually do this in person, when we actually get an applied approach of using JUnit. So, and then before and after, we'll then call that method before and after every one of those tests. Excellent. And then @test will put it as a test, something that gets tested or evaluated. And if it doesn't have any of those labels, it can be part of the class and it can get invoked, right? It can be a helper method, but it's not part of the JUnit testing directly. So it doesn't get invoked directly. So it would have to get invoked in one of your test methods if you do have methods outside of a test method. So if you want to run the JUnit test from the terminal, you can do that. You would use Java, and then JUnit itself is archived into a Java executable file, or what's called a Java archive or a jar file. So you'd want to indicate to Java that, hey, I'm going to include a jar file because it's a framework. So it's predefined code that you have to define in your class path So when you go to run code in Java, Java has some predefined class paths. Usually it's what's inside the Java directory and it's what's inside your current directory that it looks at for all the classes that it needs to run your code. But since you're going to rely on JUnit, you also have to include the JUnit framework as part of the class path. So just keep that in mind. Whenever you want to use this from the command line, you have to include wherever the JUnit jar file is at, so that Java has access to all of the JUnit's classes. And just a quick re-examination of the assertions. I told you the ones that are the most common, but just some of the other ones we have is, let's see here. So again, our module of where the assertions are in JUnit 5 is a little bit different than JUnit 4, which is where some of the other examples came from. So it's important that when you do your import, you import from org.junit.jupyter.api. And inside of this module space is the assertions package. And this assertions package is where you will be able to get all your assert methods. And so a test fails if any of its assertions conditions are not met, right? As we stated before. And some more example of asserts, we said assert equals, which has, a lot of overloaded methods. We have assert not null, you have assert true, and also assert false. So you have lots of different ways that you can try to compare your code from between the actual and the expected results to determine whether it's correct or not. And so the imports in the first few lines of any JUnit tester class, you want to import both JUnit and the assertions in the following manner. And so here is an example of how we can import that before all, after all, before each, after each, and test. And if we import it from its actualized path and its fully realized path, then we could just do at before all and at after all and at before each, and we can just use the alias of it. You could also use the wildcard for assertion so that you get all the asserts without having to name them, so you have access to them. And so test fixtures, again, it's a good idea to set up a test fixture in your test class. This is simply a known state that can be a starting point for each of your tests. So we'll look at this in more detail, but this is exactly what I was talking about. We'll look at this in actual practice, but say, for instance, in our test class, we can create a instance variable. So a private instance variable of data type animal that we'll call test animal. And then what we can do is we can create a function, we'll call it public void setup animal, that will instantiate a new animal and then bind it to that instance variable. And since we label this with the annotation of at before each, then before each new test case is invoked, this method would get invoked and it would reset whatever the old instance of test animal was that happened from a previous test case with a brand new instance. That way we don't accidentally, that way we're always testing ourselves on brand new data so that we can clearly know that each test case is not affecting any of the other test cases with the data that's being used. And so our testing paradigms here is implementation-driven testing and test-driven implementation. What you've done but up to this point is implementation-driven testing, where you write your test classes after your normal code development. So you would develop your code, then you make test classes for that. And that's fine. That helps ensure that the code that you've already written works as it's supposed to. But what's, I think, better, and what happens a lot of times in industry for the reasons that I gave you as the motivation for a team-based reasons for testing, is this concept of test-driven implementation, where you write your test cases first, where you identify what are the preconditions, what are the post-conditions, what is my input, and what is the output. And then you start developing your code based off of those requirements, because that gives you tight specifications. And then as you're developing your code, you can constantly be running it through your test class that you created. So you can actually create a test class that has the sets of inputs and outputs, and then you keep testing it. And when your code, when that class passes all the tests, and you know it's done, and you can move on to the next class or the next task that you have to do. And so you use the test to gauge the correctness of your code and whether it's done or not. And so that's actually exactly where I wanted to get today. I said I wanted to cover slides and talk about the theory of testing, why it's important, and how we do it in Java. And so I'm going to stop our discussion of JUnit testing here. And in next class, what we're going to do on Monday is we're going to go ahead and continue JUnit testing, but we're actually going to open up IntelliJ and build out a sample project, and then build a sample test class and build some asserts to actually build a test plan and test cases that exist in the test plan, so that you can see the practice of actually doing that. Excellent. So before I go ahead and end today's lecture, does anyone have any questions about what we covered today? I know it's been kind of information heavy, and so that's fine. You might need time to go ahead and grok over it and consider it. But if you do, go ahead and reach out. You can ask questions in one of two ways. You can ask me either on Discord, or you can ask me as a comment on the YouTube channel. I think either of those are valid places to put questions related to each lecture. Excellent. Okay, well, I will go ahead and end this recording then.